All right, so we're going to look at Graham's law now. And again, you have a page you can fill out over Graham's law. Um, Apparently, I'm not ready to go. There it goes. Okay, so Graham's law, which is often called Graham's law of diffusion or Graham's law of effusion, because it works for both, is based on the work that Thomas Graham did to experimentally determine the rate of the effusion of a gas, and he found it's inversely proportional to the square root of the masses of its particles. Doesn't that sound like fun? All right, so what we're saying is the speed of the gas is inversely proportional. So if one goes up, the other goes down to the square root of the mass of the particles. Okay, now this is not often calculated. I'm going to show you an example of how it's calculated. This often is just a concept question, even on the AP chemistry exam. This is treated like a concept question. Do you understand what it's trying to say? So let me go through some clarifications on how this works. First off, vocabulary. Diffusion is what we call it when a gas spreads throughout a container. So like when you spray a little air freshener in a large room. You could stand at the door of my classroom here, put in a little squirt of air freshener, and at first it's only in that corner of the room. But as time goes on, everyone in the room is eventually going to be able to smell the air freshener because it is diffusing throughout the room, okay? So that's diffusion. Effusion is similar, but that's where gases leak out of a little hole in a container. So you're not just squirting it into an area. You have a container, there's a small opening, and they are working themselves through that small opening. Very much like when you get a nail in your car tire. I've actually driven quite some time with things stuck in my car tire before I even noticed them getting low, because the hole was so small, it was taking the gases more time to leak out. And so there we go. Okay, so that's effusion. Now, I'm really not going to get picky on the vocabulary. I'm just letting you know diffusion and effusion, Graham's law works for both, and that is the difference in those vocabulary. What do we care about Graham's law? What we care about Graham's law, what you must understand is something that actually makes a lot of sense. More massive molecules, okay, the molecules that have more mass are slower. Now, they're not just, if they're twice as heavy, they're twice as slow. No, there's a square root involved there. I'll demonstrate how this works, okay? But heavy molecules move slow. Less massive, that is lighter molecules, they're going to move faster, okay? Again, there's the square root in there. So it's not like, oh, it's twice as light, so it's going to move twice as fast. It's not that way. What it really is a molecule that is 4 times lighter will only move twice as fast because the square root of 4 is 2. But Graham's law is going to be able to give you, both conceptually and via calculation, a comparative rates of movement of molecules based on how heavy or light they are. And it's not really up for you to determine if it's heavy or light. You can just put in the molar masses and let the molar masses tell you, okay? So the formula, we have an official formula for Graham's law. So the speeds comparatively of 2 molecules is equal to the square root of molecule 2 over molar mass of molecule 2 over molar mass of molecule 1. All right, that's what the M2 and the M1 stands for, molar masses, molar mass 2, molar mass 1. So it's a ratio of molar masses 2 to 1, then square rooted, whatever that division is, when you're done doing the division, you square root it, and that is the difference in their speed. Usually we take M2 to be the molar mass of the heavier molecule, and that'd be in grams per mole because you're looking that up on the periodic table. And M1 would be the lighter molecule, again in grams per mole. You're looking that up on the periodic table. Okay, so let's go through some examples. I only have 2 on your paper. I think that's all you would need to really understand this. Let's see how this is going to work out. Okay. How much faster is the average speed of hydrogen molecules compared to oxygen molecules? Well, okay, so their comparative speeds is equal to the square root, that's the square root sign, of molar mass 2, molar mass 1. Now for this, I'm going to need molar masses, so I'm going to look these up on the periodic table. Hydrogen is 1.008, so when I multiply by 2, because it's H2, that is important, 2.016 grams per mole. And oxygen is 15.999, so when I multiply that by 2, I'm going to get 31.998. All right. So I'm going to now plug it into my equation here. The relative speed of hydrogen compared to oxygen is going to be square root. Now remember, M2 is usually the heavier one. So it's going to be 31.998 divided by 2.016. Now I already have a guess. Okay. Like we could estimate that that's 32 divided by 2. And then we would square root it. So in your head, you can real fast divide 32 by 2, take the square root, you get about the approximate speed. But since I'm doing this with calculation, I might as well grab a calculator and actually get a calculated number. So I'm going to grab my calculator here, and I'm going to divide. And I get 15.87203, blah, 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 blah. Okay, and then I'm going to square root that. And I get that the relative speed is 3.98. Now there's no label on that because actually this label was grams per mole and this label was grams per mole, and they are going to cancel out each other. No label on. It's a comparative speed. Okay, let's analyze though. Like you got to understand what this answer means. 3.98, great, 3.98. What in the world does that mean? That means on average, hydrogen molecules are moving 3.98 times faster than oxygen molecules under the same conditions. So under the same conditions of pressure and volume and temperature, everything else the same, just by their nature of their masses, hydrogen is moving almost 4 times faster than oxygen. Now notice oxygen is almost 16 times heavier. So again, yes, heavier molecules move slower, lighter molecules move faster, but it's not completely just if it's twice as heavy, it's the other one's going to move twice as fast. There's a square root involved there. So do be aware, don't forget to take the square roots. Okay, now one that would be typical of something on the AP exam is actually, because that's where I got the inspiration for this from, it's actually something like this. So equal number of moles of helium and argon and neon are placed in a glass vessel at room temperature. If the vessel has a pinhole size leak, what will be true regarding the relative values of the partial pressures of the gases remaining in the vessel after some gas mixture has diffused? Okay. So here's my glass container, tiny hole in it. Now originally I have helium gas and I have argon gas and I have neon gas because originally there's no hole in it. Okay, so they're just in there. And we're told equal number of moles. Okay, well with equal number of moles we have equal pressure. So the pressure of the helium is equal to whatever it is equal to the pressure of the argon is equal to the pressure of the neon because they're all at the same temperature, they're in the same container, so same volume, and we were told same moles. So ideal gas law is going to tell us same pressure. Now, I like whatever was in the opening, stopping them from leaking, they're going to leak out. Some of the helium's going to leak out. Some of the argon's going to leak out. Some of the neon's going to leak out. Okay? Now, they're not going to leak out at the same speed because that's what we're talking about. The relative speeds are equal or inversely proportional to their molar masses. So helium, if you don't mind, I'm just going to round its molar mass to 4. Argon's molar mass is 39. Okay, actually, I think it should round up to 40, but you get the idea. Neon's molar mass is 20. Okay, so you can see we have a big difference in molar mass. So let me just ask you this. Between these four, seeing how heavy they are, molar masses from the periodic table. 4 grams per mole rounded, 39 grams per mole rounded, 20 grams per mole rounded. Which one would be able to move faster? The lighter one, right? So the lighter one's going to leak out of the container first. So I had equal amounts in the container, and now I'm going to have first place. First place of leaking out of the container is going to be helium. Lots and lots of it's going to leak through the opening and going to be outside the container. Second place is going to be the neon. A lot of it is going to leak out of the container pretty quickly, and only some of it's going to be left in the container. And then last place is going to be the argon. Because it's so heavy, it's going to leak out so slowly, it's going to be left over in the glass container. So what do I have left over in the glass containers? Okay, so afterwards, here, that's supposed to be the same size glass container. Afterwards, I should have just a little bit of helium, because most of it has leaked out, right? So a little bit of helium. I'm going to have a, I don't know, medium sized amount of neon. And I'm still going to have a lot of argon, because it's really slow leaking out that hole because it's so massive. So it's going to be, there's going to be a lot in there. So what's that going to tell us about the pressures in the vessel? Not outside, in the vessel. What's the pressures of what's left over? Well, if I have a lot of argon left over, the pressure of argon is going to be a lot. It's going to be greater than the pressure of the neon. I have a lot of argon, lots of argon left in that container. So the pressure of argon would be, I have more moles, and it's the same temperature, it's in the same volume of the container. So with more moles of argon left, I'm going to have more pressure. Ideal gas law tells us that. Then we have the pressure of neon is actually still going to be greater than the pressure of helium. Because I would expect almost all of that helium, given a brief amount of time, is going to leak out of that container, which is why it's so hard to keep helium-filled balloons to stay floating, because all those little tiny holes in the balloon everywhere, even ones so small you can't see them, are going to be leaking helium, and helium can leak out pretty quickly because it's so light. It's a very small molecule, can get through holes easily, and it can move fast. So there we go. That's also using Graham's law. Now notice I needed to use their molar masses first, and then with their molar masses, I could determine what's going to be left in my container and how are those pressures going to compare. So there we go. We can do Graham's law by calculation, and we can do Graham's law by just thought experiments. And there we go. Could I do a calculation to prove what I did down on example 2? Yes, absolutely. What would I need to do though? I would need to do a calculation to compare argon to neon and argon to helium and neon to helium. So I'm going to need 3 calculations to make that all work out. And I'd rather not, because I don't need it to answer the question. So there we go. Okay, you do have practice in Canvas that you are expected to take care of before I see you again. So be certain you get into Canvas and take care of it. And I will see you within a couple days. Good luck.